Welcome. We are discussing phase separating systems. Specifically, we were looking at delta G mix of a phase separating system with phase separating system. So, omega which is greater than 0 times x b 1 minus x b plus r t x b ln x b plus 1 minus x b ln 1 minus x b. Okay. So, this is what we were looking at, and we showed that as a function of composition in these systems at low temperatures, you can get to a state where your total delta G mix takes a form which looks like this. Okay. So, it is symmetric, it has a peak at 0.5 and it has two minima. The minima are symmetrically placed about 0.5 on either side at lower temperatures. Okay. At higher temperatures, this term is going to take over. So, this is at some temperature T1, at some other temperature T2, everything is going to become like this, because this is the only dominant term. So, this does not do much. So, T2 is greater than T1. So, this is what we were discussing. Now, delta G mix is nothing but the free energy of mixing. That is, if you had the pure A, pure B separately, you calculate their free energy, and then you calculate the free energy when they are put together in the lattice. You take the difference, this is the difference. So, if I want to know the free energy of the mix itself, then that is nothing but the total G is, suppose I have x b and the pure material B has a free energy per mole as G b plus x A, which is nothing but 1 minus x b times G A plus this delta G mix. That will be the total free energy, right. So, omega x b 1 minus x b plus r t x b ln x b plus 1 minus x b ln 1 minus x b, right. So, what is the effect of adding this term? You can see that this is just a straight line term in x b. So, that is going to add a term which is like that. So, depending on, suppose if I have pure x b, then I have x b as 1. So, this term is going to go to 0. So, I am going to have some free energy at that end. Okay. So, that is going to be the B free energy, and suppose I have pure A, in which case this term is 0. So, I am going to get the G A free energy. So, let us say that the G A is somewhere here and G B is somewhere here. Then that is the straight line expression here, which is basically weighted by the mole fraction of these two types of atoms, and on top of it you have something which is like this, which has a double well. Okay. So, this is known as a double well potential, because there are two wells with a maxima in between. So, if you add this double well to the straight line, which would have been like this, then you get a free energy expression which looks like that. So, this is the free energy curve for this system as a function of composition at temperature T1. Okay. At temperature T2, where the entropy is the most dominant term, again you can draw the free energy. What is going to happen? So, this is going to be G A and this is going to be G B, and the system is just going to form a free energy like that. Okay. This is what is going to happen at T2. So, this is as a function of composition. So, these type of curves are known as composition free energy diagrams. Okay. What is the importance of these composition free energy diagrams? The composition free energy diagrams basically tell about these systems behavior as a function of temperature. Okay. When we plot, for example, what are the phases that would exist in a system at every temperature, such diagrams are known as equilibrium diagrams or phase diagrams. So, basically the phase diagrams which tell about as a function of composition and temperature what happens in a system are derived or can be understood in terms of the free energy versus composition diagrams. Okay. To specifically talk about this phase separating system. So, let us take a closer look at the phase separating system free energy. So, it had a free energy which was like that. Okay, so, this is x b versus g at some temperature T 1. What we want to derive is basically a phase diagram which has x b versus temperature. So, T 1 is somewhere here, that is T 1. Okay. At T 1 in this system, what happens is that up to this point and up to this point here, how do I identify this point? So, if I draw a common tangent, the points at which the common tangent is touching this free energy curve, let me call them as x b alpha and that as x b beta. Okay. So, the system has these 2 points at which this common tangent is touching the free energy versus composition curve. It can be shown, probably we will do this as a tutorial, that whenever the free energy versus composition diagram develops these kind of curvature, right, concave curvature, convex curvature is okay, this convex curvature is okay. Whenever there are regions which are concave in curvature, then because if you make a mechanical mixture of composition x b alpha and a mechanical mixture of x b beta, that free energy of the mechanical mixture will always lie on this common tangent. Okay, so, that is what we have to do as a tutorial to show, but for now if you accept this statement that the mechanical mixture will have a free energy which is given by this straight line drawn between these 2 points, then if the system is in a homogeneous state, it has higher energy. By becoming phase separated into a mechanical mixture of composition alpha, x b alpha and x b beta, it can bring down its free energy by so much. So, the system at this temperature T 1 is going to make a mechanical mixture, okay, and the composition of the mechanical mixture, the composition of the phases that make up the mechanical mixture will be given by these common tangent points. Okay. So, it is going to do this at this temperature. Now, as temperature is increasing, what is going to happen? Because we know the extreme case. What is the extreme case? At the extreme case, when we are at T 2, where the free energy versus composition curve is going to look like that, that is going to become a homogeneous phase. In other words, as the temperature is increasing, these minima are moving inward and they are merging with maxima, and there is no minima or maxima left. So, everything is going to become like this. So, if you do this free energy versus composition diagram at various temperatures, at lower temperatures, this is still going to go away like this, and at higher temperatures is going to come like this. So, you are going to have a, so if I connect all these points, okay, so it will have these 2 phases alpha plus beta, and alpha composition is given by the free energy versus composition diagram at that temperature, and beta composition is given by the free energy versus composition diagram at that temperature. So, using the free energy versus composition diagram, we are going to get 2 points at every temperature except for this temperature, which is known as the critical temperature, where these 2 wells and this peak, everything has merged into one point. So, that is why it is a critical point, above which it is going to have a homogeneous random substitutional solid. So, that is what is going to prefer here. But the moment the free energy versus composition diagram develops some concavities like this, in those regions it is going to phase separate. So, this is the phase diagram, okay, of a system that has this type of behavior, this type of phase separating behavior. So, this at T 1 for example, when it reaches these 2 equilibrium composition and makes a mechanical mixture, we say that it has phase separated, that is, it has become into 2 phases, one is alpha, the other one is beta. Alpha is A rich, beta is B rich. So, the system which was homogeneous, if you prepare it even as a homogeneous system, it is going to go into two phases and it is going to form a mechanical mixture of these two phases. Of these two phases, one is rich in A, the other one is rich in B. Okay. The regular solution model gives a very symmetric phase diagram as you see here. So, this is known as a phase separating system, and this is also sometimes known as miscibility gap, because there is some immiscibility. If the two atoms are completely randomly distributed in the solid solution, then you will have a completely mixed system, but that is not what we are seeing here. We are seeing that the system would prefer to become immiscible. So, it is like mixing water and oil, they do not mix. All the water molecules come together, all the oil molecules come together, and they always form these two phase mixture. So, you have oil somewhere, water somewhere, oil somewhere, water somewhere. So, this kind of gap, it is known as a miscibility gap. So, in this region complete mixing is not possible, and as usual, like everything else in thermodynamics, the reason why complete mixing is not possible is because if you actually do complete mixing, the free energy increases, but if you have a mechanical mixture, the free energy decreases. So, the system is always trying to minimize its free energy. So, it knows that whenever your free energy versus composition diagram develops these kind of concave curvature, it has to undergo phase separation and become a mechanical mixture. Okay. In mathematics, this kind of procedure that we have used. So, you say that the composition will change like this, and then it will be a mechanical mixture like this, and then composition will again change like this. So, because this region is beta and this region is alpha. So, this is known as convexification. So, we do not want any concave regions in the free energy versus composition diagram. If they are there, we convexify it by drawing a straight line, which is a common tangent line between these 2 points, and that is the process known as convexification. Okay. So, the first step in phase field models is to understand equations which describe this phase separation process that is happening. Okay. That is the basis of phase field models. The first problem that Kahn and Hilliard tried to solve is to understand this phase separation mechanisms. How does it happen? Okay. Does it happen by nucleation and growth, and if so, how should it behave? And they found that it is not behaving like that. So, they had to modify the usual growth description, which is using Fick's law or diffusion equation. So, basically that is where we are going to start. So, we are going to be seeing a lot more of phase separating systems and free energies which have this kind of concavities in the days to come. Okay. Thank you.